So welcome to Math 349, lecture 31. And so what I want to do for the last few weeks of the semester is just keep going through material that's either directly related to the chapter that you're writing for the book or related to what you're doing for your math outreach project. And so there was a request to do from Pascal to calculus. So given that this is a 300 level class, I will assume everybody here is comfortable with 1 and 2 variable calculus. And so the purpose of these notes was to try to introduce calculus to some young kids. So these were kids who had done, I think, just Algebra 1 at the time, and maybe not even a full semester of Algebra 1. They might have been in the midst of doing Algebra 1. And so the question is, how do you get to the key concepts of calculus without getting bogged down in the details? And again, it's much easier when you are giving a discussion with somebody because you can get a sense of what are they strong at, what are they weak at, what are they comfortable with, what have they seen. When you're writing, you do not have that advantage. Does anybody know what the big idea is from calculus? I'm going to say Calc 1. What's the big idea in first semester calculus? Derivatives. Be more specific. What about the derivative? It's the rate of change. The tangent line. So the tangent line is really the fundamental idea that locally, whatever function I give you looks like a line. And that's why on the picture over here, you can see I've got some curve and I've drawn a tangent line. This is actually a very important picture. This is Newton's method to find roots. But the key idea is that if I give you a complicated function, we can understand it by understanding it locally as a straight line, as a linear function. Now, depending on how low you go, the kids may not even have seen much in terms of functional notation, in which case there's no way you're going to get to calculus without first introducing them to, well, what do we mean by a function? What do we mean by, I have some rule that you give me an input, it gives you an output. Two outputs cannot come from the same input. Each input goes to one and only one output. Okay, so hopefully everyone has seen Pascal's triangle. So I'm going to skip a lot of the stuff over here. If you're writing this chapter, there's going to be far more here that you can pick and choose from. And so it's all about how things change with time. So when you're writing something up, you can actually talk about some examples of things that people might have seen. So can you think of anything that people might have seen that has some kind of change as a function of time related to yourself? Any physical properties of yourself? Height. So where do you think your derivative is going to be largest? Yeah, when you're young. When you're young, each month you're going to be going significantly more. At our age, we're hoping that the derivative is just 0. When you get to my age, there's the danger of it actually becoming negative, and you start to get a little bit smaller, which you see. So this is a nice way to just try to connect to people something you've seen. Younger people are growing at a faster rate. Do you think that the rate of change is constant, that it starts off large and gets small and small and smaller uniformly? Or do you think it sometimes gets small and then gets larger? The latter. Why? Okay, but why? What biological process? Puberty. Then you get your height explosion. So again, try to find ways to connect depending on the audience. How might you have seen something like this before? And you're not going to expect to see the rate always constantly decreasing. Okay, so hopefully you've seen Pascal's triangle. The simplest way of defining it is we've got 2 expanding diagonals of 1, and then every number is the sum of the number immediately above to the left and above to the right. So for instance, 6 would be 1 plus 5, 15 would be 10 plus 5. There's a tremendous wealth of properties here, and these numbers also have combinatorial interpretations. So you might have seen these numbers as n choose k. It's how many ways can I choose k objects from n when it does not matter the order in which I choose them, only that I've chosen them. Okay, so when I have something like this, we have the opportunity of asking lots of questions. You can ask people, can you find any structure in this? So there's the hockey stick result. Can somebody tell me what 1 plus 2 plus 3 plus 4 equals? Which is the number immediately down and to the right. What's 1 plus 4 plus 10 plus 20? Yeah, and at this point, you might not even be adding them. You might just be immediately going bottom to the right. How many of you have seen the hockey stick lemma before? Okay, so this is something that you've now just seen. Can you come up with a proof? Can you prove that when you sum along these lines? Can you find other formulas? What can you prove? And so it's never a bad idea to try to give people some opportunities to see what can you find. Okay, hopefully everybody is comfortable with FOIL. Do they still use that word when teaching you? First, outside, inside, last. One of the nice things about something like this is you have a definite procedure. The more explicit something is, the harder it's going to be to screw up. And when you're young, it's very easy to screw things up if you have a little mnemonic like this to remind you, how am I supposed to do things? When we get older, we have an incredible wealth of bad habits, of things that we do because we've been working on it so long, we can afford to be careless. We can do things maybe in a different order because we know it's going to cancel out nicer. But in the beginning, if I want to multiply things out, I can just use FOIL. And so does anybody have any idea why might we want to be talking about FOIL in a lecture from Pascal to calculus? Yeah, we're going to be looking at x plus y to the n or x plus h to the n. You were setting the stage for what's going to be coming on later. And so you have to decide at what point do you want to start mentioning stuff like this? Why are we going to want to use something like this? Well, we might have a pure polynomial, pure monomial like x to the n, like x cubed, x to the fourth, x to the fifth. For young kids, it might be a little bit hard to imagine an arbitrary power, so you might do things with a definite power. And why do we care about this? Well, we're going to look at rates of change. So we're going to look at maybe what's going on at the point 7. So we might have 7 to the n. And then what happens if we move over a little bit? So we'd have maybe 7 plus 0.001 to the n. How would we calculate that? And so, these are ways to expand things out. And you could maybe begin to start talking about, as we put in smaller and smaller numbers to move away from 7, as we look at the deeper and deeper terms, it shouldn't matter that much. Now, this is, of course, just multiplying 2 numbers by another 2 numbers, right? We have a sum of 2 times the sum of 2. You can, of course, generalize this. So what are the 2 ways we could generalize this? We could have n numbers times n numbers. That's one way to do it. What's another way we could do it? Right, or we could have more products, right? We could either have more summons or more products or both. And so one of the ways to prove some of the results in general is through grouping in parentheses. We proved this for basically the distributive law for 2 summons times 2 summons. If I had 3 summons times 3 summons, well, in the 3 summons, I could group the first 2 together. And now I have 2 summons times, if I group the first 2 and the next one together, times 2 summons. And so by repeated uses of FOIL, we can actually come up with stuff like this. And again, you have to decide how much of this is worth getting into. Depending on your audience, if they're not budding mathematicians, they may not care. This is the difference between a math professor and a math student. So you have to really think, how much do you want to get into? What kind of problems do you want to put? And you could ask people, what would FOIL look like for 3 summons times 3 summons? What would FOIL look like for 3 products? Okay, and then we can explicitly go through and we can calculate x plus y squared, we can calculate x plus y cubed. And what's nice about this is there's several different ways to do x plus y cubed. I think the easiest way is to note that it's just x plus y times x plus y squared. And so if we've already calculated x plus y squared, there's no need to calculate it again. So what this tells you is for a lot of things in mathematics, sometimes it's easy to calculate intermediate values, intermediate steps. Now, if I only care about x plus y to the 10th, then maybe I don't want to compute all these things beforehand. But if I care about all the stuff beforehand, especially for those of you who are taking computer science, this can become a great way to compute as you go. And now you start to notice the 1, 2, 1, the 1, 3, 3, 1, and we're beginning to see the coefficients from Pascal's triangle. How many of you are comfortable with the proof of Pascal's triangle? Okay, so we can start to think about combinatorial implications. So we'll talk about this more later, but does everyone agree that when we expand x plus y cubed, I'm only going to get terms involving products of x's and y's. No z's are going to suddenly show up. What's the highest exponent x could have? 3. And what's the lowest? 0. And then the one that's a little bit more interesting is whenever I have a term involving x's and y's, the sum of the exponents must be 3. It has to be exactly 3. And the reason is I have 3 factors, and for each factor, I choose either an x or a y when I expand things out. So I know I'm going to have something that looks like some multiple of x cubed plus some multiple of x squared y plus some multiple of xy squared plus some multiple of y cubed. Yes? The sum of the coefficients will be 2 to the n. And do you know how to prove that? So you can put in any value of x and y. What would be a good value of x and y to put in so that you would get the sum of the coefficients? Yeah, if you put in x and y equals 1, you get 1 plus 1 cubed. And there's the proof. So what's great is this is a great observation. I notice that if I look at the sum of the coefficients, what if I look at the alternating sum? 1 minus 3 plus 3 minus 1. What's the alternating sum equal to? 0. How can you prove that? Yeah, if you look at 1 minus 1, 1 minus 1 is just 0. So we can prove immediately here that the sum of the coefficients is going to be 2 to the n, and the difference of the coefficients is the alternating sum of the coefficients is going to be 0. We all agree that it's going to be some polynomial where the coefficients are not necessarily known. Does the polynomial have to be symmetric in x and y? Sure. So we all agree that we have some polynomial involving x's and y's, right? Okay, good. It's punched. So we're going to have something, x cubed plus something x squared y plus something xy squared plus something y cubed. And this is going to equal x plus y cubed. What I'm asking is, when you look at the polynomial that arises, does it have to be symmetric in x and y? Whatever the coefficient of x cubed, that's the coefficient of y cubed. Whatever the coefficient of x squared y is, that's the coefficient of x y squared. Why? But why does the polynomial have to be symmetric? So if we call this f of xy, okay, equals x plus y. Oops, I get an add. So we get x plus y cubed. So we have the following. I claim that this is equal to f of yx. If I switch the roles of x and y, they're the same. Why would that be the case? Now, do you agree that if we actually look at what it is, it's 1, 3, 3, 1, that it's symmetric? We all agree that it's symmetric, yes? The question is, how can you see that from first principles? Okay, so which operations? Okay, so which addition? You gotta be very specific. Treat me like a moron. Which real number addition? Which integers? Which ones? X plus y. How else could you write x plus y? Y plus x. That's why it's got to be symmetric. Because x plus y cubed is the same as y plus x cubed. If I switch the order of x and y, then in my expansion, I flipped the roles of x and y. That's why it has to be symmetric. So before I do any calculations, I know whatever the coefficient of x cubed is, that's the coefficient of y cubed. Whatever the coefficient of x squared y is. If you think about it combinatorially, what are we doing? When we're multiplying things out, I have a bunch of factors. For each factor, I either choose an X or a Y. Right? So if I choose X, has anybody read The Sneetches by Dr. Seuss? Okay, what kind of Sneetches are there in the world? There are two types of Sneetches in the world. There are those with stars on their bellies, and there are those that do not have stars on their bellies. And eventually, what do you think we realize? They go through a machine and they keep changing as to who has a star and whatnot. And what do you think we all realize at the end of the day about having a star or not having a star? It doesn't matter, right? But for a while, people think it matters. If I'm telling you I'm choosing from the first and the third factors to be X, that's the same as I'm choosing to exclude Y from the first and the third, right? If I'm choosing X, I'm excluding Y. You can see that there's a lot of symmetry here. And so when you're looking at the factor X squared Y, it's coming from all the times I chose X twice and I chose Y once. Well, choosing X twice and Y once, if I flip it around, for the places where I chose X, I now choose Y. The places where I chose Y, I now choose X. There's going to be a nice one-to-one correspondence. And I'm never going to count the same thing twice. It's never going to give me the same, so it's going to work out like this. This is another way to see things as symmetric. If I have X plus Y cubed, I have three factors. For each factor, I have to choose either an X or a Y. And that's where the 2 to the n is going to come from. I have two choices for each one. 2 times 2 times 2 is 8. So again, we're going through a lot more detail now than you would probably do if you were writing this up. But I want to give you some options for things you can think about. And just in general, when you're doing exposition, which ways can you go? There's so many things you can open up when you're discussing. Okay. All right, so we talked about seeing the coefficients from Pascal's triangle, and then how would we prove that? One thing, of course, is to start by gathering data. And as we start to gather data, we begin to see that this is reasonable. One way is to go by induction. And then, of course, the question is, have the kids seen induction before? You could do it by introducing the notation of binomial coefficients and choose K. You can do this purely algebraically. And so I'm going to skip some of these things over here. So let's say we know X plus Y to the 5th, and we have X plus Y to the 6th. So it's just X plus Y times X plus Y to the 5th. So it's X times X plus Y to the 5th plus Y times X plus Y to the 5th. And now we multiply everything out. And what you notice is when I hit X plus Y to the 5th and multiply by X, I still have the same coefficients as before. I'm just increasing all the powers of X by 1. And when I have the X plus Y to the 5th and I multiply by Y, I have all the same coefficients as before. I just increase the power of Y by 1. So now the sum of the indices, the sum of the exponents is now going to be 6 rather than 5. And when I add them together, notice that, okay, I'm going to have just X to the 6th from here, nothing else can give me an X to the 6th. I'm going to simply get just a Y to the 6th. But for everything else, I'm going to get two contributions. One coming from the first factor, X times X plus Y to the 5th. One coming from the second, Y times X plus Y to the 5th. And that's my sum. My sum of the coefficient above to the left and above to the right. And this is a proof of where that's coming from. I don't need to know that these are the binomial coefficients. I can just say whatever they are. When I try to get to the next level, the way I get to the next level is by just adding above to the left and above to the right. So it's important to remember when you are trying to prove things, depending on the audience you have, you can use very different arguments. With people who have done some basic, probability or combinatorics, I would definitely talk about n choose k and saying, well, look, when I'm expanding out x plus y to the 6th, if I want the term x to the 4th y squared, I choose x 4 times, I choose y twice. So I have 6 factors. How many ways can I choose 4 of the 6 factors to give me an x? That's 6 choose 4. And then the remaining 2 factors both have to be y's. That's 2 choose 2. But what's 2 choose 2? 1. That's why we never bother writing it. We will just write it as 6 choose 4, not 6 choose 4 times 2 choose 2. But there really is this multiplication by 1 going on. So for students who've got a stronger background, I would definitely talk like that. But for younger kids, it's enough to just talk about, we can see when we're expanding things out. Okay, Just as an aside, some of you I know have seen this from me in previous classes. A fun property of Pascal's triangle, I'm going to put a dot if the number is odd and a blank if the number is even. So this is what Pascal's triangle looks like after 4 levels. This is what it looks like after 8 levels. And then I've since fixed these plots. I was, a little bit lazy the first time I did it in Mathematica. It was easier to draw things horizontally rather than vertically. So what I'm doing is I'm drawing more and more layers, more and more levels of Pascal's triangle, but I'm fixing it so I always display it in a rectangle of the same size. So I keep squishing things down. And if you want, you can go online and you can watch the video, and I'll send the link to this, which goes through and you start getting a nice fractal shape. So depending on the audience you have, you can talk about some beautiful hidden properties of Pascal's triangle, coming in with fractals. Okay, so the next part of the talk is shifting to algebra and limits. And if you go into schools, the algebra backgrounds of students may not be as high as you would like. I think that's the polite way of phrasing it. Basic algebra skills are often very much in need of additional work. A lot of schools have a lot of math interventionists to try to help like this. If you can't do the basic algebra, it's going to be hard to do the stuff that relies on this. When I teach multivariable calculus, one of the topics I love is Lagrange multipliers. The amount of multivariable calculus you need for Lagrange multipliers is minimal. You take a gradient and you say gradient of f is equal to lambda gradient of g. You have the constraint equation, and now you have n+1 variables, n+1 equations, and you solve. Well, you solve by doing algebra. And most of the time, the students have no trouble doing the multivariable calculus. It's actually doing the algebra and finding the answers. So when you're teaching stuff like this, you'll always be aware of what might be the background of people. So, starting off is just talking about how would we evaluate a function? What does it even mean to talk about evaluating a function? Well, function is a rule. You give me an input, I give you an output. Why do you think we use the letter F to denote function? Starts with F, right? And then when we do calculus, we'll have F prime for the derivative, or we'll have big F for the antiderivative. We're choosing names for functions that are related to the original function to remind ourselves that they're related. So always think about what you want to name things. So a linear function is going to be something in the form ax plus b, where a and b are fixed. And so we can talk about specific examples and talk about how to evaluate them. It's not bad, since we're going to be doing so much with lines. That's the big idea, is that locally any function looks like a line. Let's just write down an explicit formula. Here's an equation of a line. F of x is 3x minus 5. Let's put in a couple of values and get a sense of what it looks like. And you can start to see, if I move x by 1, how much are things changing? And you should see that it's always changing by 3. And this is a great opportunity to start talking about what is the slope of a function? What is the slope of a line? Okay, we can then do a quadratic function. A little bit more complicated. Choose one for definiteness. Say 2x squared minus 3x plus 4. And now notice that as we increase x by 1, the behavior is much different. It's not always changing by a fixed amount of 3. Sometimes the function is actually decreasing, and then it's increasing, and then the rate of increase is increasing. So, very different behavior, and you need to decide just how much time do you want to spend on something like this. Notice that a quadratic function is going to be a lot harder to analyze than a linear. If I know how fast I'm traveling, and I know where I start, and I'm traveling at a constant speed, and I tell you how much time has elapsed, it's very easy to tell me exactly where I'll be at that point. Just take where you were and multiply by your speed times the elapsed time. For quadratic function, it's much harder to do that because your speed is constantly changing. All right, so we can then talk about plotting different polynomials and have hopefully get a sense of what they look like. It is extremely easy for people to just manipulate symbols without understanding what they're manipulating. So which is larger, x cubed or x squared? Which is larger, x to the 100 or x to the 5th? Not necessarily. Depends on the x. So for what x would x to the 100 be greater than x to the 5th? 2. What else? Give me all the x where that would be the case. X is greater than 1. Right? So you've got to be careful. When x is less than 1, they actually flip as to which one is larger. And so here is a plot, and I think I can zoom in a little bit. Yes. And so you can see that, for small values, the linear function is beating the quadratic is beating the cubic. But then for larger values greater than 1, they flip as to which one is greater. And again, there's probably a mindset that people are, for the most part, thinking about evaluating these functions at integers, but you want to break them of that habit immediately. If we're doing calculus, we're not just evaluating a discrete set of integers. We're evaluating along the continuum, arbitrarily small changes. And when you're doing this, a linear function will be larger than a quadratic or a cubic for very small values of x. Because if you're a small number, then when you raise it to a higher power, it's going to get even smaller. So again, just trying to think about what you can do to give people a sense of what things look like. So now we need to talk about limits. And how many of you did limits rigorously in your first calculus class? Or did they basically just say, I just look at it, and does it kind of look like they go together? Yeah. How many of you have not taken real analysis? Not taken. So basically almost no one here has done real analysis. Okay, so if you're going to be a math major, at some point that will change. And you will take real analysis. And you will see rigorous notions of limits. Okay, and you have to decide, depending on where you are, how much detail do you want to get into? You can spend so much time doing everything so rigorously that you don't get to the good stuff. And so you have to balance with, well, what am I going to do in the first class? And then just tell students in a future class, you can go into more theory and do this more rigorously. But for now, this is pretty good. And just be aware that you have to make sure that it's done solidly. I like to sometimes give examples of paradoxes or things that seem right but are actually wrong, to just alert students to the need to do things rigorously. So if I give you a polynomial, say 3x plus 5, what's the limit of f of x as x approaches 2? So can someone tell me what that limit would be? It would be 11. And you're not doing some elaborate, epsilon delta analysis. You're just saying, I just plug in x equals 2. And as long as everything is well behaved, we can just do that. We can just plug in the value, and that's going to give us the limit. Okay, I could give you other things. So if I want to calculate, I could write x as maybe 2 plus h if I want to figure out what's the limit as x approaches 2. And so it would be 2 plus h, with h getting smaller and smaller and smaller. And so now if I put this in, what would f of x be? Well, that's f of 2 plus h. So I can expand that out. And then that would be 3 times 2 plus h plus 5. Or just when I do the algebra, 6 plus 3h plus 5. Okay. And then you want to basically say the limit of a sum is the sum of the limits. The limit of a product is the product of the limits. This is not always true. As long as at least one quantity is finite, it's true. So if I give you the limit as x goes to infinity of x minus x, what does that equal? 0. But I wouldn't want to write that as the limit as x goes to infinity of x minus the limit as x goes to infinity of x, because that would give me infinity minus infinity. What if I gave you x squared minus x? What would that limit be? Infinity. And if I gave you instead x minus x squared, it'd be negative. So I can make these limits whatever I want. So you've got to be careful when you have infinities involved. And so over here, I want to basically say, look, I want to calculate the limit of essentially 11 plus h, 11 plus 3h. And I just want to say the limit of a sum is the sum of the limits. That has to be proved. But I think people would be willing to give you that. You can just say, look, you have to show that this is true, but this seems reasonable. Okay, and so we can calculate that and we'll get the exact same 11 that was said earlier. Right, so now when we compute a limit, we say as x approaches 2. And it's extremely important to remember that x is never allowed to actually be 2. It's just allowed to get closer and closer and closer. It can get as close as it wants, but it's never actually equal to 2. So what if I give you x squared minus 4 over x minus 2 as x goes to 2? Can anybody tell me what that limit would be? Or does the limit not exist? You could, but this is from Pascal to calculus, so we haven't hit calculus yet. So, again, you can drop the atomic bomb if you want, but can you do this without L'Hopital? It's 4. Why is it 4? So we can factor the top. And so if we factor the top, we can write it, so I think I might say that at the end. Yes. So we could have noticed that x by x squared minus 4 is x minus 2 times x plus 2. And if we do it like that, we can cancel the x minus 2's because x is never equal to 2. X is just getting closer and closer and closer, but it's never actually equal. So if you are able to observe that, you're in great shape. If not, I can replace x with 2 plus h. And then when I expand everything out, the numerator becomes 4 plus 4h plus h squared minus 4. The denominator is 2 plus h minus 2. So when the dust settles, we get the limit as h goes to 0 of 4 plus h equals 4. So we can actually calculate this limit without too much trouble. We just replace x going to 2 with x equals 2 plus h and sending h to 0. Why can't we say the limit of a quotient is the quotient of the limits? If I want to calculate the limit of x squared minus 4 over x minus 2 as x goes to 2, why don't I just say the limit of a quotient is the quotient of the limits? Yeah, we're dividing by 0. We're not allowed to divide by 0. And so that's why we can't say the limit of the quotient is the quotient of the limits. And that's why we have to go through this longer process. Okay. Not all limits are easy to compute. In an earlier lecture I was giving to some of the kids, we got the following, which are formulas for pi. When you look at this, you might have a conjecture of what comes next. Right? Any thoughts on what might come next? Yeah, probably 128. And what about the denominator? Yeah, it looks like every time you go down, you add another term in the denominator. And it's going to be basically like 2 plus the square root of the previous term that you had. So there's a nice, well-defined pattern here. And I claim that this is going to converge to pi. Good luck showing it. Now, it's actually not that bad to show if you know the geometry that was used to come up with this. And so I'm basically doing approximations to the area of a circle. So I know it's going to be converging to pi. But when you look at it like this, if you can see pi coming out of this, more power to you. I cannot. And so it's not always easy to figure out what is the limit. And we need to have good procedures to evaluate things like this. Okay. So now let's move on to part 3, Introduction to Calculus. We're going to start talking about differentiation. Okay. It's almost a requirement, I think, that when you start talking about differentiation, you use average speed. You may lose your math license if you use another example. All right. This is, did everybody start this way? We have somebody who's running, somebody who's driving, somebody who's flying. You know where they are at every moment in time. And so you want to figure out how fast are they traveling at a given instant. This is the canonical example that everybody uses. Okay. And so we can ask lots of different types of questions. What's our average speed? What's our fastest speed? What's our slowest speed? What's our most common speed? Then, of course, it's which questions can we answer? Well, depending on how much detail I give you about the function, we can answer all of these, right? The more information I have, the more I can deduce, but it might become difficult. So if I just tell you where you are at every moment in time, it seems like in principle, I should be able to figure out where I was going my fastest, where was I going my slowest, what was my average speed. But some of them are going to be a lot easier than the others. So the average speed is going to be the easiest one. And so, to calculate the average speed, we just look at the total distance traveled, we divide by the total time elapsed, and we get our average speed. This is a good opportunity to remind people about units, right? How many of you, it's often done, I think, in chemistry. In my day, it was called factor labeling. Does that phrase make sense to anybody? where you try to keep track of what the labels are of everything so that at the end of the day, you don't just have a number. You have a number with units attached to it. What should the units of speed be? Miles per hour, kilometers per hour, centimeters per second. You could be crazy and do furlongs per fortnight. As long as it's a distance divided by a time, that's acceptable. And so at the end of the day, when I do 110 divided by 2, I could write this 110 as 110 miles divided by 2 hours. And then that would give me 55 miles per hour. And that's a good way to make sure that you're not making a mistake. There's a lot of integrals. If any of you are planning on going off to graduate school in mathematics, I will be careful because this is being recorded. You may have to take the graduate records exam, the GRE. You can solve a lot of their problems by just putting units in the integral and then seeing that only one of the proposed answer has the right units. And if anybody's interested, email me and I'll send you some stuff on that. All right. How would we compute the average speed? Well, what we do is we look at how far have we gone, f of b minus f of a, and we divide by how much time has elapsed. And this will give us the average speed. And all we need to be able to compute this is to know how much time has elapsed and how far we've gone. That's not a huge ask. That's basically just saying, I need to just evaluate the function at these endpoints. Now, if I want to try to calculate the instantaneous speed, what would be a good definition of instantaneous speed?
H goes to 0 after.
Yeah, so as the time interval gets smaller and smaller and smaller, the average speed should be converging to the instantaneous speed. And so then the question is, can we do this limit? And so the first thing is we try to do it for a linear function. So we can calculate the average speed. And if you go through and you do the algebra for the average speed for a linear function, you get 3. And so it shouldn't be that hard to calculate the instantaneous speed if the average speed is always 3. We can now calculate the average speed for a quadratic function. And we can go through and we can do the algebra again. And so I'm not going to read through the algebra, but when you do it, you get that the average speed from A to B is B plus A plus 3. Okay, so there's a part that's independent of the endpoints, but there's also a part that depends on where you start and where you end. So for a quadratic function, it's not constant. And of course, you could then ask, is there a formula for cubic? And so on, and so on, and so on. All right. And so the average speed, this is just, okay. So now we could ask, what happens in the limit as B goes to A? What would the average speed become as B goes to A? It becomes 2A plus 3. So this is the instantaneous speed. It's 2A plus 3. If you look at the function is f of x is x squared plus 3x plus 1. You know calculus right now, right? What's the derivative? Since you know calculus. 2x plus 3. Do you see that over here in the 2a plus 3? Of course. There's the 2x plus 3, we're just evaluating it x equals a. So now, if it doesn't know calculus, this is your chance to ask them, do you see how you get 2a plus 3 from x squared plus 3x plus 1? Now, for this particular problem, we did the algebra. Instead of doing x squared plus 3x plus 1, we could look at some other functions. And we could try to get a sense of how does it depend on the coefficients. More generally, I could give you, say, alpha x squared plus beta x plus gamma, and ask you to figure out what those are and see how things come into play. When you're looking at this, of the coefficients x squared, the coefficients of 1, 3, 1, and the powers of x are 2 and 1. Which number does not seem to be coming into play with the instantaneous speed? I'm sorry? The 1. Does that make sense that the 1 is not coming into play?
We know that 1 is x to 0.
If you know, well, okay, but then you're using your calculus knowledge. You don't know calculus at this point.
There are no x's.
There are no x's. What is the plus 1 doing? Graphically, what does the plus 1 do to the function? it shifts it all up by 1. So this is your chance to talk back about, well, when I'm plotting a function, what did the various things do? The +1 just picks everything up by 1 unit. And so this is going to affect f of a and f of b equally. So when I subtract, the 1 is going to cancel. So it makes sense. You could also try to make the argument that when I'm trying to figure out what's going on, it's enough to do it for just a pure power. And then just put them and piece them together. Do it for the function 1, do it for the function x, do it for the function x squared, do it for the function x cubed. And then figure out, well, if I have 3x squared minus 11x, I know how to combine them. Okay, so calculating the average speed, it's never a bad idea to have some tables and some plots. And so I'm trying to calculate what's the average speed from x equals 1 to b. And we'll take the limit as b is getting closer and closer and closer to 1. And so you can see that the average speed, it looks like it's converging to something. What might you guess the average speed is converging to? 5. Now it blows up when I put in b equals 1 because it's undefined. What you could then do is you could then zoom in and go from 1.0 to 1.1 in steps of size 0.01 and see how things are changing. And getting it closer and closer and closer to 5. And so there's plenty of stuff to have you start to conjecture what the answer is. So now we just make rigorous the notion of instantaneous speed. It's going to be the limit as b goes to a, or if we write b as a plus h, we can go through, and here's our definition. And so this is f prime of x. Everybody here has taken multivariable calculus, correct? This is not the definition that generalizes best for multivariable calculus. So there's a slightly better definition of the derivative than this. And so I will just put this in right now. I only know one person who has ever learned calculus where they actually were told that this is not the definition that generalizes well. Anybody want to guess who that one person was? My daughter, yes, right? There's an experiment. So we can look at it as the limit as h goes to 0 of f of x plus h minus f of x minus f prime of x times h over h equals 0. So if I look at this, what am I saying? F of x plus h, I subtract off f of x where I am, I then subtract off my instantaneous speed times how much time has elapsed. So this part that I'm subtracting over here is basically my prediction of where I should be. And I'm comparing that to where I actually am. And then I'm saying that the prediction is so good that even when I divide by a small number, the amount of time that's elapsed, that still goes to 0. Because again, if I didn't divide by h, of course it's going to be close, because since h is small, the f prime of x times h is going to be a small number. So f of x plus h is basically f of x by continuity. So of course it's going to be close. So I expect the numerator to be small. It's not a big deal that the numerator is small. Okay? The fact that it's small when I divide by h, that's amazing. Now, if you look at what goes on, I have an f prime of x times h over h. That's just f prime of x. So if I look at all of this part over here, I can then just bring that over to the other side as f prime of x. That's why this is really equivalent. And the correct definition in multivariable calculus is, instead of doing f prime of x, what we would do is we would first of all, we would put in absolute values. No, that's not a big deal. And then the h would become the length of our vector, and we would do the gradient of f at x dotted with h. That would be how we would replace the f prime of x times h. Okay, and so h would be a vector of small changes, and then the h in the denominator, we would replace that with the length of h. That's the correct generalization to several variables. In one variable, we don't have to worry about any of these issues. Okay, so we now have a notion of the instantaneous speed. And so we can calculate the instantaneous speed. And again, whenever you do stuff like this, you should always do it for simple problems first. When you proved, force of habit. How many of you were in a calculus class where they proved the fundamental theorem of calculus? Okay, not many hands. So when they give you the fundamental theorem of calculus, they tell you that the integral from a to b of f of x dx is big F of b minus big F of a. This would be stupid without the following: is if this is a and this is b, this is the area. So if I didn't tell you that this quantity over here is the area, then this could just be a definition. The fact that this is the area under the curve and it's found by the antiderivative, where the derivative of big F is little f. So when you're given the fundamental theorem of calculus, you can try it on some simple functions. What's the simplest function you could try for little f? Nope. Nope. Simplest. 1, right? Then you try it for x. And so if you try it for 1, that's a rectangle. Oh, it's poorly written, but. So I will just draw a rectangle over here. If you try f of x equals x, what do you get? What shape? Triangle. Great. We have determined areas of rectangles and triangles. If that's what the fundamental theorem of calculus is giving us, this is not cause for celebration. Once you get to x cubed, however, or x squared, so x squared, you're now having the area under a parabola. And now it's an accomplishment to actually compute that. It can be done. One way to do it is by induction and dividing things up. These are the Riemann sums. But now you have a way of seeing that the fundamental theorem of calculus is giving us some real content. So over here, we can calculate the instantaneous speed for linear functions. And we go through and we do all the algebra, and we see that if we have something in the form 3x plus 5, it's going to just become 3. So more generally, we can start to ask, why are we getting the 3 here? Where is that coming from? And it looks like it's coming from the coefficient in front of the linear term. And you can go through and you can prove that. Then we can look at more generally, what if you had something in the form cx plus d, figure out what that would be. And now I'm going to stop here. You can then ask the kids, what do you think it might look like for here? And we can say, maybe we could break it up into 3 different answers. The answer coming from 2, from 5x, and from 3x squared. And we already know the answer for 2 of the 3 parts. What's the 3x squared going to give us? All right, so this is a good place to stop.